So this is the prediction of tidal-driven coastal currents using, here it is, convolutional neural networks, which sounds very impressive. Again, TCOM's Hian researcher, Choo, Jian, Feng, who's going to present. Go ahead.
Good morning, everyone. Welcome to my presentation. I'm Jian from TCOMS. And today I would like to present to you our ongoing research titled Prediction of Tidal-Driven Currents using Convolutional Neural Network. So in this presentation, I'll first give a short introduction, followed by the methods that we use to test CNN, and then the results, and lastly, conclusion. So, most shipping accidents are caused by human error, and these accidents have severe economic and environmental impact. So some examples are the 2021 Suez Canal blockage, which reported a loss of $54 billion. And another example would be the 2018 Sanshi accident, which reported 136,000 tons of oil being spilled in the South China Sea. So one possible solution to this is to build an autonomous vessel that travels optimally and safely to its destination, using fast and accurate current forecasts. However, access to this forecast is often unavailable in remote ocean areas. Furthermore, predicting currents of small time intervals and space are too complex and expensive when using physics-based models on board. Hence, our objective is to develop a machine learning model that provides cheap, fast, and accurate predictions of currents for self-driving vessels on board. So the machine learning algorithm that we explored in this research was convolutional neural network. So convolutional neural network is a machine learning algorithm that maps its input to its output using the given 2D or 3D dataset. So it is widely used in image processing applications such as facial recognition software and also even Tesla's full self-driving software. And right now, we would like to take the advantage of CNN as well to predict 2D currents. However, applying CNN to hydrodynamics is relatively new. Hence, we need to lay a foundation first as a start so that in future we can build more complex models. So moving on to methods, I'll first give a brief introduction on astronomical tides, then the domain that we are going to predict our 2D currents. And lastly, I'll go through the two methods that we devised to test CNN's capability on feature extraction from hydrodynamic datasets. So tides are periodic in nature. They are caused by the Earth, Sun, and Moon orbital system. And the main phenomenon found in the waters of Singapore Straits, shown in the video on the right, is mostly tidal-driven, with a period of around 12 hours. And the domain where we'll be predicting our currents is the area around St. John's Island, which is located at the west of Singapore. So first, to create the training dataset for the time series method, we use Mach 21 FM, which uses the 2D depth average Navier-Stokes equation to compute the 2D time series of our currents and surface elevation around St. John's Island. And the data type of the input and output of the CNN model is 2D time series. And the input and output are made equal to each other because we want to reduce the uncertainties from the input and output mapping first so that we can focus on testing CNN's capability in capturing the complex flow in the dataset. So for the time series method, we created three types of CNN models. So the first is the one input to output model, followed by the two input to output model, and lastly the three input to output model. So the reason why we have these three models is because we know that the currents and surface elevation have a physical relationship. And we want to see if CNN can capture this relationship. So now we proceed on to the creation of a Fourier method dataset. So first, we simulated multiple 2D time series of varying Manning number using Mach 21. We then convert each 2D time series into its amplitude, phase, and frequency. And lastly, we convert this amplitude and phase into Cartesian coordinate. So each current and surface elevation will have their own respective x and y component. And the third dimension of each data set is now, instead of varying time, is varying in Manning number. So the data type of the input and output of the CNN model would be a 2D x or y of a single Manning number. And the input and output will also be made the same as well. So for the Fourier method, we will only be using the one input and output CNN model. So in the results section, I'll be going through the time series method first, then followed by the Fourier method results. So when comparing the streamlines between the numerical model and the CNN model, we found that the CNN model could predict complex currents quite okay, although at certain times the CNN model couldn't predict the currents correctly. And also when comparing the different CNN structures for the time series method, we found that when we introduce surface elevation to any of the U or V velocity, the CNN model performance actually decreases. So this shows that CNN may not be able to capture the inverse relationship between the currents and the surface elevation correctly. So, moving on to the Fourier method, when comparing the streamlines of the numerical model and CNN model, we observed that the model could predict the currents very accurately. So, in conclusion, CNN can actually capture complex flow patterns accurately. However, CNN may not be well suited for time series prediction because CNN is more for still image applications. Hence, the non-sequence data type, such as the one shown in the Fourier method, works a lot better. It is also found that CNN performance reduces the data of the CNN performance reduces when data of inverse correlation are used together. And to take a step forward in the development to predict currents in a domain, we can try using conv-error TM models for time series prediction so that we can also predict phenomena such as storm surges. And we also could develop a physics-informed neural network model for higher accuracy when including all three hydrodynamic variables together. So that's the end of my presentation. Thank you.
Thank you. Okay, time for questions. Anybody have questions? Online, don't have any questions. So obviously your presentation was extremely clear. Just for the benefit of non-experts, could you explain the Manning number and how is it determined in actual field data?
Manning number is really related to the bottom surface roughness. So if your bottom surface roughness increase, then there will be more dissipation, which means your wave energy will decrease. Yeah.
So then on any given day, how do you decide which Manning number to apply?
This is as a start, we just use Manning number as a varying parameter, yeah, to test CNS capability.
Okay. Anyone else have questions? Further questions? Okay, if not, then thanks, Jeng Feng.
Thank you.